In this video, I'm going to introduce ASR, which is automatic speech recognition. When we speak to a phone, generate automatic captions, or transcribe an interview, a computer has to convert a continuous acoustic signal into a sequence of words. This process is called automatic speech recognition, or ASR. In this short introduction, I will explain what ASR is, how a more modern system works, how we evaluate it, and why the same system may perform differently across speakers and recording conditions. ASR can be defined as the task of mapping spoken audio to written text. The input is not a neat list of words. It is a continuous waveform containing information about pronunciation, timing, voice quality, and background sound. The model therefore predicts the most probable text given the audio. To do this well, it must recognize words, use linguistic context, and handle variability such as accent, speech rate, noise, and microphone quality. So ASR is better understood as a probabilistic sequence prediction than as simple audio recording. A simplified ASR pipeline begins with the audio waveform. The signal is converted into a time-frequency representation, often a log-mel spectrogram, although some models learn representations more directly from the waveform. A neural encoder then transforms the input into contextual speech representations. The decoder predicts a sequence of tokens such as characters, subwords, or words, while using both acoustic evidence and linguistic context. Finally, the tokens are converted into a transcript, often with punctuation and timestamps. In modern end-to-end systems, many of these stages are optimized jointly rather than built as completely separate modules. Earlier ASR systems used several separately designed components. A Gaussian mixture model and hidden Markov model represented acoustic patterns, while a pronunciation dictionary and a language model helped connect the sounds to words. Deep neural networks later improved the acoustic model, but kept much of the same pipeline. End-to-end approaches, including CTC, attention-based encoder-decoder models, and RNN transducers, reduce the need for separate hand-built components. Recently, large self-supervised and weakly supervised models have learned from massive and diverse speech data, improving multilingual transfer and robustness. The most common evaluation metric is word error rate, or WER. We compare the model's hypothesis with a human reference transcript and count substitutions, deletions, and insertions. The total number of errors is divided by the number of words in the reference. In the example, sat becomes sit, and 2 words are deleted, so the WER is 50%. Lower WER means better transcription accuracy. However, WER is sensitive to text normalization, and one average score cannot tell us whether errors are concentrated among particular speaker groups, accents, or recording conditions. ASR is now used in many settings. It supports voice assistants and hands-free interfaces. It produces captions for videos, meetings, lectures, and interviews, which is especially important for accessibility. In professional contexts, it can assist with call center analytics, medical dictation, and documentation. ASR is also useful in language learning and research because it can provide pronunciation feedback and help create searchable spoken corpora. In all of these applications, the quality of the transcript directly affects the quality of the next task. ASR errors are not random. They often appear when the test speech differs from the data used to train the model. Accent and first language background can affect pronunciation patterns. Faster speech may contain reductions, connected speech, and disfluencies that are difficult to segment. Noise and poor microphones can hide acoustic cues, while overlapping speakers create competing signals. Domain-specific names and technical vocabulary may also be rare in the training data. This is why robust evaluation should compare performance across speaker groups and conditions instead of relying only on one overall average WER. To summarize, automatic speech recognition is a sequence modeling task that converts a changing speech signal into written tokens. Modern systems increasingly learn the acoustic and linguistic parts of this process together using large neural models and diverse data. WER provides a useful starting point for evaluation, but meaningful analysis also asks who produces the errors and under what conditions. Thank you for listening.